How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to be discussing Etherchannel, or port channels, link aggregation groups, lags, whatever term you want to throw at it. That's what we're going to be discussing in this video and all the cool stuff that goes along with it. So we're going to start from the top and work our way down in terms of its operational value and stuff like that. So you can configure port channels, and that's what I typically refer to them as, because, well, actually, it's interesting. If you're on a Catalyst switch, it's called an Ether channel. If you're on a Nexus switch, it's called a port channel. If you're on a Palo Alto firewall, it's an aggregated Ethernet. If you're on Juniper, I think refers to them as lags. A lot of different networking vendors refer to them as lags. But whatever term you apply to it, you are trying to take two or more interfaces on a device that connects to another device and do what they refer to as link redundancy. So there's link redundancy, and then you have node redundancy. If you are doing link and node redundancy, you are trying to take things way farther than you really need to in some cases, but in other cases, not far enough. So we'll talk about that more in detail here in just a moment. So when we talk about how this comes into play, there's a couple of things that you really need to remember when it comes to how this actually works. So there's a couple of prerequisites that you need to have in place. Number one, that the mode or the operational type of the port channel is the same across all interfaces. There is a distinct difference between the mode and the state, meaning what is the state of the link? Is it a port channel, or sorry, is it an access port or a trunk port? And then what is the mode that it's running in? So is port channel running are we working in a static, or are we dealing with a dynamic operation? So when we talk about that, there's got to be some things that line up. You can't have two different states working in a port channel. You can't have one access port and one trunk port. They have to be the same. If it is an access port, both interfaces need to be configured for the same VLAN. If it is a trunk port, all of these same VLANs need to match. So we'll talk about that in more detail later, but it's actually very straightforward. I really don't need to go much further than that. If you've got two interfaces and you've got trunks configured, if one's got one more VLAN than the other, then the port channel is going to fail. Now, there's the concept of a member interface. So member interfaces are the interfaces that will eventually make up the Ether channel, and then you have the logical interface that will basically control the two member physical interfaces. So when I say that, I literally am meaning gig 0/0 and gig 0/1 on switch 1 and 2. These two interfaces are what we are going to configure in a port channel. Now, I will do port channels over in the bigger site once we get there, but for right now, this is as far as we're going to take it. So, from an operational perspective, when you are configuring your port channels, there's two different types of port channels that you can create. Ether channel, excuse me. Again, I spend a lot of time on Nexus, so I'll have to apologize in advance if I say port channel too much. When it comes to an Ether channel, you've got two different ways of configuring. You have the static version, where you are telling it's going to be channel group 1 mode on, for example. That would be the syntax that you would use, where you are just statically configuring the port channel, or the Ether channel. I'm going to call it port channels because the port channel, Ether channel, they mean the exact same thing. So when you're configuring it, you would statically configure it on both sides. Now, both sides have to have equal configuration. So if both sides are going to be, both sides, it's going to be both switches. The number of the port channel that you assign to that particular bundle is unique to that switch. They don't have to match on either side. So if you wanted to use port channel 2 and port channel 3, you could. That information is not exchanged back and forth. There is also a way to do it dynamically through a layer 2 protocol called the Link Aggregation Control Protocol, or LACP. That's what at least a lot of people refer to it as. There's also PAGP. PAGP is the Cisco proprietary version, and as you notice here, there is no reference to PAGP at all in the documentation or in the bullet points of the blueprint. So I'm not going to really dive into it. PAGP and LACP operate the exact same way. The only difference between the two, and they're configured the exact same way. They have all the same prerequisites. The speed and duplex has to be the same, full, like 1 gig full, 10 gig full, that type of stuff. The access port must be the same on both interfaces. The same amount of VLANs on the trunk, that type of stuff needs to be the same. The only difference between PAGP and LACP is the terms used. So in most cases, you're not going to use PAGP. I have never used PAGP in production. I have always used LACP. And that is because when I am working with other vendors, non-Cisco, for example, I've configured port channels to Palo firewalls, HP switches, Dell switches, you name, pull a vendor out of your hat, and I've configured a port channel to it. But it's easy, you know. There are cases where you're going to want to go static, but in most cases you're going to go LACP, because LACP, there is a BPDU that's specifically coded for LACP, and it's basically a hello mechanism that goes back and forth between the switches to make sure that the interface is on. So if something happens and there's a failure in the hardware on one side of the switch, of the port channel, LACP is going to detect that and take down the port channel. So you actually want to have that in place, because if you don't, you run into the potential of you not catching it and the port channel staying up, even though that's black holing traffic. So that's one of the key reasons why you would do that. Now, operationally, there's really not too much more to them other than that. So you can do a layer 2 port channel, which means that you are doing VLAN or trunk on your port channel, and go that route with it. So you're doing some sort of layer 2 forwarding. But there's also a layer 3 port channel where the port channel interface actually gets an IP address. So you can do, and in order to make a layer 2 port a layer 3 port on a switch, you type in the command no switch port at the logical level. So the idea would be to go configure these interfaces in a port channel, right? So you gig 0/0, gig 0/1, they would be given LACP and channel group mode 1 active, and that's the other thing we'll talk about here in just a minute, active versus passive. And then what you would do is you go down to port channel 1, interface port channel 1, you type in no switch port, and that would convert the layer 2 port to a layer 3 port, and you'd be able to give it an IP address, and then the whatever routing protocol BPDU or routing protocol hellos would be able to ride over both interfaces. And there are load balancing algorithms that you can attach to globally in the port channel configuration that will allow you to determine how the port channel is actually forwarding traffic. I've never actually monkeyed around with that, so I've never had to go in there and make an adjustment for it. I'd have to go look up the documentation to give you specifics on the details to each one of them, because I honestly have never done anything with them from a load balancing perspective. So the other thing to keep in to talk about is going to be Etherchannel misconfiguration guard. So just like we talked about the error disable recovery when we were talking about BPDU guard in a previous video, what we end up doing with Etherchannel misconfiguration guard is if there is a failure somewhere inside of the port channel process, what will end up happening is the port channel will be taken down. So I'm going to see if I can't attempt to influence a failure, but in most cases I'm not able to. So there might be something that happens down the road where we might see it, but for the most cases, I know well enough configuration-wise the order of operations that are needed in order to make that work. So I don't normally ever have a problem with that. So the last thing to talk about is identify multi-chassis Etherchannel use cases. So you're going to see the term, and I'm going to bust out my pen tool here and go over to black because it's easier to talk about here. you have this concept of what they refer to as the single chassis ether channel, and then you have the multi-chassis ether channel. And essentially what the difference between the two is with single chassis ether channel is you have two switches that are like this, and then you're running two connections between the two. So each one of these links right here would be a 1 gig SFP fiber connection or Ethernet connection. What they are doesn't really matter. Now, what ends up happening from a logical standpoint, there is an icon that is going to be used in order to dictate that this is a port channel. And what you're going to do is you're going to do this. You're going to draw a circle around the lines. What this typically refers to is there's a bundle. So, whether you're using the term LACP, port channel, ether channel, lag, whatever, a bundle, because literally every, iOS XR refers to it as a bundle. Palo Alto refers it to as an aggregated Ethernet, right? So regardless of which term you use across it, they all basically end up meaning the exact same thing. It's a port channel. It's a bundle. So multi-chassis ether channel is used when you have multiple upstream devices, and then you have a singular or even double devices down here. Now what ends up happening is this device right here, so 1 and 2, are talking to each other somehow. Whether this is a stack-wise on 37 or 90, a Cat 9300s or 3750s or 3800s, whatever model switch you happen to be using, that's how that would come into play. Now your higher model switches like the 9500, stuff like that, they're going to be using a virtual switch link. They've made changes to the terminology lately, and I don't keep up with it as I used to. So back in the day, there used to be this concept of a stack-wise, where literally there was a cable that plugged into the back of the switch that was a defined cable, and it was referred to as a stacking cable. And the idea was to join the control planes of both switches together so that they would look like one switch logically, but physically it was two different switches. And what would end up happening is whatever your port range on here is, whether it was a 24 port, whether it was a 48 port, whatever the case might be, this would be switch 1, this would be switch 2. And the nomenclature would be 1/0/1, 1 through say 48, and then you'd have 2/0/1 through 48, so on and so forth. Well, you would continue doing that, and you could add pretty much as many switches as you wanted to. I think the most I've ever, documentation says 9 last time I read it, but operationally speaking, I would never recommend going that high. I have done as many as 4 in a stack, but it gets complicated because that's a lot of individual switches. That's 96, that's about 192 ports. So that's a lot of interfaces to keep track of. So you have that case. Now, for older model switches like the 4500, the 6500, you have this concept of known as a virtual switching system, or VSS, where you would do basically the same thing, but you wouldn't have a dedicated cable. What you would do is you would join the supervisor engines together, and they would use a virtual switch link to do the control plane synchronization between both switches. So if you connected a device over here to this switch and to this switch, and then formed a port channel over the top of it, just like we would do here, these two are both considered multi-chassis ether channel solutions because of the fact that they are taking a singular device and attaching it to two upstream devices. So if I was to take switch 3, switch 1, and switch 2, and create a stack between switch 1 and switch 2, and then I was to do a port channel there and a port channel here, that would be a multi-chassis ether channel design, because I'm connecting multiple chassis together in an ether channel scenario in order to give myself both link and node redundancy. When I am trying to bundle two switches at the switch level together to provide redundancy, if one fails, the other one takes over, then that is what they refer to as a link and node redundant design. This right here is something that you are going to see a lot in production. Port channels are everywhere. And if you're not using a port channel, you should be questioning why you're not. So the other thing that I want to talk about real briefly before we get any further along is that I talked about spanning tree and how you're supposed to build triangles with your environment and not squares. And what I mean by that is this. If I have a scenario where, what is this? Oh, there it goes. So if I have a scenario, and actually let me switch colors over to white so it's easier for you guys to see. So if I have a scenario from a spanning tree perspective where I am building squares, right, let me draw it this way here. So I've got 4 devices, right? Just like I would right here, up here. I've got 1, 2, 3, 4. And if instead of building it like a triangle, like this, I decided I was going to build this. And maybe I even add more links down here. Just because of the fact that, and I actually just ran into this with a customer not too long ago where they had this going on, where they had connections everywhere. And it was actually rather complicated to try to pick it apart. So what ended up happening was when we eventually picked it apart, we realized that they built squares in their layer 2 environment. And so what was happening was we would have asymmetric forwarding. There was all kinds of slowness. Traffic would be going this way. Traffic would be going this way. It was all over the place because of the fact they built squares. And they had blocking ports in the places that they shouldn't have had them. It's just overall bad design. So when we talk about building layer 2 networks, we should really build them in triangles. So, and if I didn't mention this in the spanning tree section, I apologize for not talking about that from a design perspective. But this is essentially what you should be building. You should always be building triangles wherever you want, wherever you can, so that the upstream links from the access to the distribution level, the uplink from access to distribution, these guys are always good. These are always open and forwarding traffic. The only time you should be blocking is between here and here. This is the only interface that should be blocked is the one sitting between the switches if they are not aggregated. So if they are aggregated and this is they're stacked together, then this link right here is just there for if something comes in on this interface and for whatever reason it needs to go out this way. Maybe the uplink this direction is down. And then you need to ride across the interswitch link to the outside world. And that's a lot of the time that's how Nexus VPC works. And we're going to talk a little bit about that when we get over to the larger site for continuing on with Etherchannels. But this is essentially what you want to do. You want to build this right here. Build your network in triangles. If somebody challenges you on this, make sure you reference back to this and say, this right here is a crap design. Do not ever, as a network professional, build squares in your layer 2 environment. Always build triangles. Do not ever connect your access layer switches together unless you have an overwhelming need to do so because somebody did something they shouldn't have done. And an example of what that might be is, for whatever reason, you need to connect this switch here that is somewhere in the network to this switch over here directly via some sort of fiber or Ethernet cable in order to get something moved. I've had to do this 2, maybe 3 times in my career because the customer didn't give me the information that I needed, and one particular time I had overlapping subnets and I needed to interconnect the two in order to solve an ARP issue. So there are times when you have to think outside of the box and do things you normally wouldn't do, but you still do them because you need to get the job done. So that's essentially the reason why I say, best practice is this guy right here. I'll say BP. So BP is best practice. Always build triangles in your network wherever you can. Now, my personal opinion on this whole thing is whenever you can, don't use layer 2 networking unless you absolutely have to. So if you have to do layer 2 networking with spanning tree, VLANs, trunks, it's going to be around. You're not going to be able to get rid of it, especially in the campus access layer. You're always going to have it. Unless you've got a very big budget and you have a new technology friendly team that is willing to go take a risk on something new like Cisco's SD access, or I'm not sure if any other vendor has has a campus like VXLAN ACI type of solution out there now, but SDA became a big deal, and that's essentially what if I had if I had things my way, that's the direction I would go with it, because I would get rid of layer 2 out of the gate. Layer 2 would be gone because it's easier to work with layer 3 than it is layer 2 in my opinion. So at least that's how I view it. So that is essentially what you need to keep in the back of your mind when you're thinking about layer 2 networking. That's what you need to know. Now that we've talked about that, and I feel like I've rested my case as to why you should do things a certain way, that is what I would do. Excuse me. So what I'm going to do is I'm going to go ahead and clear out the screen. That is it for this video. If you guys have any questions, please leave a comment in the comment section down below. And if you haven't already done so, please like, share, and subscribe. And I'll catch all of you fine people in the next video.